When you prompt an AI tool and it instantly pulls the exact document you need from a sea of millions, it feels like magic. But beneath that surface, there is a harsh physical reality. To find that perfect match, the system has to measure the mathematical distance between incredibly heavy data points inside its active memory, or RAM. At the core of a data block is a 32-bit floating point number. It stores 7 decimal places of extreme precision, consuming 4 bytes of memory. Now, scale that up. A single high-quality vector is built from a grid of 1,024 of these hyper-precise numbers. When you multiply that heavy architecture by a billion items, that extreme precision devours terabytes of expensive, power-hungry memory. It creates a hard, physical ceiling on how large our AI systems can grow. Loading these precise vectors into active memory is like a passenger boarding a commercial flight with a house-sized suitcase bursting at the seams. The brute force solution is to just buy bigger servers, but for software operating on a global scale, relying on massive, expensive hardware quickly becomes physically and financially impossible. Engineers face a massive tension here. The system needs to search billions of ideas instantly, but the extreme 7-decimal accuracy of the numbers is actively choking the computational pipeline. To scale these systems up, we have to do something highly counterintuitive. We have to intentionally discard precision to make these models lean enough to actually use. The solution is a mathematical process called quantization. Think of it as vacuum packing the data, deliberately shrinking those hyper-precise numbers down into low-bit approximations. You don't need a 6-decimal GPS coordinate to navigate your neighborhood. A solid city block address gets you there. Applied to data, this is scalar quantization. Just as a 16 million RGB space maps to a 256 color palette, our vectors map to smaller integers. The mathematical yield here is enormous. Converting those 32-bit floating point numbers into 8-bit integers slashes the entire memory footprint by a factor of 4. The database is still storing the exact same fundamental concepts. They are just compressed into a cheaper, slightly lower resolution format that finally fits into the overhead bin. There is an obvious catch. If we compress the numbers and lose all that precision, doesn't that ruin the database's ability to accurately measure the distance between ideas? Actually, the database never unpacks the data. It calculates similarity directly within that quantized space. These smaller integers fit perfectly into modern CPU registers. Instead of calculating one heavy number at a time, hardware processes massive batches simultaneously, letting smaller blocks slide right through. The cost for this technique is minimal. In practice, moving down to 8-bit integers results in a nearly imperceptible 1 to 3% drop in search recall. The system willingly trades a microscopic fraction of accuracy for lightning-fast parallel processing. It removes the memory wall that keeps most large-scale vector searches from running on standard hardware. This shift in efficiency means a 16-gigabyte database can rapidly collapse down into a highly efficient 1-gigabyte footprint. That reduction has an immediate geographic consequence. Advanced AI architecture is no longer trapped inside massive, expensive, centralized server farms. This compression enables edge deployment, where complex models can operate locally without a constant link to a data center. We can now run semantic vector search natively on offline mobile phones, budget devices, and directly inside a web browser, processing everything entirely within the physical borders of the device itself. When you vacuum pack your clothes, they might come out of the bag slightly wrinkled, but that slight loss in crispness gives you the ability to carry them absolutely anywhere. In the era of massive scale AI, absolute precision is a trap. Strategic approximation is what allows us to push these models out of the server farm and into the hands of the people using them.